Right. So in these additional examples here, let's just try to convert the equation, the parametric equations, into Cartesian equation. So we want to convert, okay, or write. All right. And we are not aiming to make the sketch of this or whatsoever. So we just want to convert that into a Cartesian equation. This is a very vital skill that I want to keep enhancing your experience like that. So the one set of equation we have here, sine of t. All right, so go ahead and spend some time writing it down right there. All right, so in this set of equation right here, we have x equals 3 cosine of t. And so it has some similarity with some of the earlier examples that we have already studied, right? It got the cosine involved here, and then the y value has the sine involved. Now, only one cosine and then one sine right here. The other one is a 1/2 sine of t, okay? And so, no, so the ultimate fundamental, again, is to eliminate the t variable. So now in a problem like this, where x equals 3 times cosine of t, anytime that we see the sine or the cosine involved, the experience that I've been getting is that we can just simply solve for the cosine and solve for the sine by itself. So here the easiest route, we got x over 3. I'm dividing both sides by 3 right here, okay, to equal cosine of t. Okay, so we divided both sides by 3. And that's why the 3 cancel on the right hand side. So I ended up with, yes, x over 3 equals cosine of t. And let's leave it there for now. Okay. So we don't directly solve for t, but we just, try to, if I'm talking about this kind of problem right here, is in that special family of parametric equations where it has the x equal to a cosine or a sine, and then the y equals to the other trig function right there. Okay, and then here what we have, see in here, I want to solve for the sine of t by itself, so we're going to need to multiply both sides by 2 right here. So 2 times y equals 2 times 1/2 sine of t. Okay, and so the 2 here cancel with that 2, so that we're leaving behind 2y, right, equals sine of t. All right, so now that's what I meant earlier. See, anytime that our parametric equation involves, the x equal to one of the two fundamental trig functions, it could have been sine here, and then the y value, the y variable equals to the other trig function. If it's a cosine here, then y is a sine. If it's a sine here, the y is a cosine, but only one of the two in each of the x and y. So we want to solve for the sine and the cosine, the sine and the cosine separately. So get rid of the coefficients. And so now, again, we come back to that fundamental understanding: cosine squared of t plus sine squared of t, we always equals 1. Okay, and so right from that, so now cosine of t now is x over 3, and so cosine square, we're going to come out with x over 3 all square. Okay? So once again, because cosine of t equals x over 3, and then the sine of t equals 2y. So now sine square of t in this equation has to become 2y all square. Okay, so x over 3 all square plus 2y all square, all of that equals 1. Okay, so now right here is our Cartesian equation. You can rewrite this as x squared over 9, right, plus, and here we can have 4y squared, right, that equals 1. And this is our final equation right there. Okay, it's a Cartesian equation just fine, and you can also stop at this equation here. This is also, again, your Cartesian equation already, but I prefer to write it down into this more simplified form like that. Okay, so that's keep building better experience for us in terms of these sine and cosine related. Right. All right, so let's look at another one. So right here is our new problem right here. So x of t is some 3 sine of t, and then y of t equals 3 cosine of t. All right. So for this set up parametric equation, very similar experience right here. Think about x equals 3 sine of t. So just like what I said earlier, the x value equal to one of the two fundamental trig functions of t right there. And then the y variable equals 3 times the other fundamental trig function. So we got this time we switch over between x and I mean sine and cosine. But it's okay. But it's just once again one of the variable x here equals one of the two trig function, and the y variable equals the other one. So now the usual work that we've done, similar to similar to a lot of examples, kind of standard. We divide both sides and we solve for sine and we solve for cosine, like how I mentioned that. So x over 3 equals sine of t. Okay. And then in that way, y over 3 equals cosine of t. We divided both sides by 3. Okay. Cancel the 3 here. So there's that general fundamental that we want to solve for sine and cosine separately. And then once again, from there we go to sine square of t plus cosine squared of t, famously known to be equal 1. And so in this case right here, sine of t equals x over 3. So we have x over 3 all squared plus, now cosine of t equals y over 3. So cosine squared of t in this equation will become y over 3 all squared equals 1. So that is our Cartesian equation already. But we want to think about algebraically step a little further. So that is the same as x squared over 9 plus, now y over 3 all squared. You can think of that algebraically as y squared over 9 again, equals 1. So that is another form of our Cartesian equation. I can take this just fine. Okay. But then this equation, since it has this Cartesian equation that we have arrived here, since it has that common coefficient here, that common denominator here, we can think about multiplying both sides of this equation by 9 like that. So multiply 9 to the right, multiply 9 to the left hand side, it's going to cancel out the two terms. See, scratch work is showing like this. X squared over 9 plus y squared over 9 equals 1. So if we multiply 9 to the right hand side and we multiply 9 to the left hand side, the 9 here cancel with these 9s. And the 9 here multiply with the right hand side being 9. We're looking at x squared plus y squared equals 9. Okay, and so the same equation, now we can algebraically, according to that work right here, we can turn that into x squared plus y squared equals 9. Another even more simplified version of the Cartesian equation. Same equation, but just a more rearranged version and making it more simplified. Okay, but then from this experience right here, allow me, on the same example, same problem, allow me to show an alternative solution. The observation here is that right from the beginning here, well, yeah, it has that fundamental, I mean, it has that form where x of t and y of t, the x of t equals one of the two trig functions. There's a sine here, and y of t is equal to cosine the other trig function. Okay, but then in this problem, what's special about this problem? It has the equal coefficient in front. Okay, so when we observe, after observing this as an alternative solution, so I'm talking about we having an alternative solution right here. Okay, a different way of approaching it. So we have x equals 3 sine of t, and then y equals 3 cosine of t. So the alternative solution I'm talking about here, you can directly think about, you can directly square both sides. So x squared here can become 9 sine squared of t, okay, because we can square both sides. Think about x squared equals 3 sine of t all squared. See, squaring both sides, squaring the left hand side gives me just x, squaring the right hand side, the whole right hand side gives me just that See, square of the 3 is 9, square of the sine of t is sine square of t. So that's how I get like that. And so the same way I'm going to square the left and the right hand side of this other equation, 3 cosine of t all square. And that will come out y squared equals 9 cosine squared of t. All right. And so in this case right here, then we can have, think about x squared plus y squared. We can purposely, sometimes it's all about we're exploring things around. So we can think about x squared plus y squared will equal 9, because x squared is equal to 9 sine squared of t. So 9 sine squared of t, okay, plus, now y squared here will equal 9 times cosine squared of t. So that is for sure, right? Because x squared plus y squared will definitely, we bring in, will equal to this, because we bring in the meaning of x squared, I mean what's equal to x squared, substitute that in there. And what's equal to y squared to substitute that in here. But then from this right hand side, we can further see that, hey, we can factor out a common factor. So we got 9 here, factored out, and then sine squared of t plus cosine squared of t, right? And so now we realize that, hey, sine squared plus cosine squared is a 1. So here we're looking at just simply 9 times 1 equals 9. And so now all of a sudden we realize, hey, this x squared plus y squared from the beginning will equal all the way down to 9. Like that. And so now we come to our final Cartesian equation, x squared plus y squared equals 9. That is another way of how we can recognize the Cartesian equation for that for this system of the parametric equation. All right, and you can see that I keep giving examples that have those parametric equations that deals with the sine and the cosine, because at this time point where we're learning this, I'm not very sure how far you guys will go in your mathematics career and in your mathematics path. But as you advance to Calc 1 and Calc 2 and eventually at Calc 3, you will see this kind of parametric equations a lot like that. And that's why I want to keep building up that example, those experience for you guys. All right, and so, and when it comes to these examples right here, it's impossible to cover all examples out there. So I decided to be done with these kind of examples, the kind of examples where, in the end, we're just converting from parametric equations down to a set of Cartesian equations. Okay. So now when we're working with parametric equations, there's also a skill that's worth our attention. Okay. Parametrizing graph. All right. Parametrizing a graph. What it means here, parametrizing here means, what it means here is we want to be finding a set of parametric equations, okay, from a graph. That's the idea, from a graph. But then the intention behind the scene is that the graph, okay, the graph with known Cartesian equation. All right. So that's what parametrizing a graph means. So you're given a graph. So any graph has some known Cartesian equation, and then we want to go from that to the Cartesian equation, and we want to put that back into the parametric equations again. And so that's the skill that we want to get in as well. So how about we call it example 4 right here. Okay. 3x plus 5. All right. And now allow me to add in this particular open parentheses right here. How about graph provided? I'm going to quickly hop onto the computer screen to show the graph like that. So this equation right now is the 3x. I mean, y equals 3x plus 5 is a Cartesian equation, and I will show the graph right here. The graph will be provided for this. And so clearly you can see that, see, the instruction of the example number 4 here, and it's one class of big problems, so that's why I put that as an example with a number over here. But we want to find the parametric equation. That's why it's, see, finding a set of parametric equations. the work we're doing here is called parameterizing. Right? We are parameterizing a graph because the graph will be provided with this equation. So anytime we have a Cartesian equation, there will be a graph coming along. That's why commonly people refer to that as parameterizing a graph. But it also means the same as finding the parametric equations for a given Cartesian equation like that. Okay, so that commonly means the same thing: finding parametric equations for the graph or finding parametric equations for the Cartesian equation that's given. Okay. All right. So right here is my graphing space. Okay. So my graphing space is here, right? And then y equals 3x plus 5 is the Cartesian equation that we wrote on the board. So let's look at the graph right here. So no one is surprising to see this graph. Okay. So this graph in red right here is the graph appears to be a line, right? So as far as the graph, it's a line, and this graph right here has Cartesian equation y equals 3x plus 5. Okay, so now with the graph being shown now, right, we want to find, instead of staying with this Cartesian equation, we want to find the parametric equation. We want to find one way of how we can write the parametric equations for this. So I want to emphasize one thing, that when we're finding, see the wording of what I'm saying right here, when we're saying that we're parameterizing a graph right here, the meaning of that is we're finding a set of parametric equations. That means we can have multiple ways of doing that. Okay, there are multiple final answers. There can be, different final answers right here. So allow me to show the most trivial solution right there. And then there are going to be some other solution that take some creativity out there as well, that will give the exact same graph but completely different look of the parametric equations. So now let's dive into the most trivial solution right here. So the graph we already saw on the board, right? So now let me call it the Cartesian equation. So we saw the graph, but in the end, see, the idea for this trivial solution, anytime you're looking at the graph, you got to know the Cartesian equation that comes with that. So the graph we had earlier in this problem, we already had the Cartesian equation given right here. So y equals 3x plus 5. So the trivial solution I'm talking about, the easiest way to get to is we're going to purposely set x, right, equals t. X equals t. So x equals t means, yes, your function x of t is defined as just t. You already had the parametric equation for x. And then in that way, think about it. If x equals t, y equals 3x plus 5, but x equals t, so that means you can substitute the t for the x right here. So that means your y here has to consequently becomes 3 times t, right, plus 5, because we're substituting x by t. And so that means now we produce for ourselves, hey, and wait a minute, that means y equals 3t plus 5. So we come to a conclusion, hey, so some function y in terms of t can be written as 3t plus 5. And so now we have for ourselves one way of writing the parametric equations. X of t equals t, and y of t equals 3t plus 5. You already have for yourself a set of parametric equations. I'm not saying that this is the only way. I'm not saying that this is the only way, but this is the most trivial way, like that, the easiest solution. So the generality here is that anytime your variable, anytime you have your equation that's separated into two sides, one side is only in terms of one variable and the other side is in terms of the other variable, like that. Okay, and then we can solve for one variable, we can solve for one variable in terms of the other one. So here y is already expressed as an expression in terms of x only. And so in that way we can treat the independent variable as x equals t. And then we take the dependent variable to be just y of t to be that expression in terms of t. Okay? And so in that way right here, allow me to reinforce that experience. Let's call the problem just now part A. Okay? And then we can go ahead and we can do this. We can call that now part B. Okay, so how about x equals, right, 5y squared minus 1. Actually, putting this 5 is a little too much. So how about just 2y squared minus 1. Okay, so we have for ourselves the Cartesian equation, and the graph will be provided so that you can have a look at the graph. All right, so with the computer, on the computer screen, here's the equation x equals 2y squared minus 1. So the graph looks like this. It's a sideways parabola. Okay, it's a sideways parabola. But now, so we saw the graph, right? So now when we're talking about parametrizing that, finding the parametric equations, my observation is that the graph that we've had has the corresponding equation, the Cartesian equation x equals 2y squared minus 1. So it looks like in this equation, yes, x and y are separated into two separate sides like that. And then what I'm seeing further is that in this equation, y is being regarded as the independent variable. We can treat y as the independent variable and x being the dependent variable. So now I'm going to enforce my explanation of what I've done earlier. So in part A, the very same here. In part B here, I'm going to tackle down right on the independent variable. The independent variable y, I'm going to start out with that first. I'm going to let y equals t. That's the idea about the trivial solution right there. So y equals t, that means we immediately have y of t, right, as a function equals the simple function t. But then in that way, if y equals t, our equation here will become x equals 2 times, right? We're substituting t in for y, so we got 2 times t squared minus 1. And that will be 2t squared minus 1. So we come down to x of t can be written as a function of t being 2t squared minus 1. And so in that way, we have x of t equals 2t squared minus 1, and together with y of t equals t. Okay? That's our set of parametric equations for this sideways parabola. All right. And so we built our foundation on being able to recognize, the parametric equations from a given Cartesian equation. Okay, so that's that's what we've been doing, is the primary skill we want to build in this example 4. And now once we've had that from example 4 right here, okay. All right, so now once we've done that kind of skill that we've learned in example 4 right here, we want to really get into parameterizing an actual graph. So let's now call that example 5 right here. Okay. So we want to go with find the parametric equations for the given graph. All right, so for the given graph. So I'm going to swing over to my the computer screen. Go ahead and take some time writing this down. And then when you're all done, I'm going to swing over to my computer screen to show the graph. And then make sure you make a good close enough copy of the graph like that. All right. So let me show the graph here. Okay. So this is the graph here. It's a straight line. The graph that we have is a straight line, and pay attention to these intercepts right there. Okay, and it's a straight line. Okay, so spend some time copying down the graph like that. Make sure to make good label on these intersection points like that, these intercepts here. And I purposely hid away the actual Cartesian equation for this, because we just want to start from scratch. Here we go. Here's a graph, right? It's being a straight line. It's got a couple of characteristics right here that we can recognize, and that's it. Let's find the parametric equation for that given graph. Okay. All right. All right. So the plan for that now is we got to be able to pinpoint. We got to be able to write down the actual any Cartesian equation for that given graph. So like I said, we got to be able to pinpoint and write down any Cartesian equation for that given graph that we saw. So let's look at the graph one more time right here. the graph is a straight line. So any straight line has a slope, right? So this slope right here, it looks like it's what? From this point to the other point right here, it's got, see, 10 over, right, and 5 up, like that, right? So 10 over and 5 up. So with this line right here on my board, right, I can easily resketch that right here. See, minus 10, right, and then 5 is here, okay, on the y-axis. And so the line connects through those two intercepts. And so clearly in a line like that, right, the slope here has to be, the slope here is, see, up 5 over 10 run. So the slope here, see the rise over run thingy, or the fall over run that we've learned from the earlier algebra courses. And so now it's going to be a slope 1/2. So we got the slope, right? And so being a line, and at this point you guys are at this level right here, you should have quite a few flexibility to get the equation of a line. Once you've had the slope right here, you can take advantage of one of these 2 points. Your line here goes through that point, being this point here specifically 0 for x and 5 for y. Or this point here, the line also goes through that point here, being negative 10 for x and 0 for y. We can take advantage of either one of these. Let me take this one here, okay? So in what we've learned, any line has a point slope equation. Okay? So point slope equation. That's just one way of how you can write down the equation of our graph right here. And the equation we're about to write is a Cartesian equation. So point slope form of this line right here gives me this. How about y minus, see this point right here, I chose that point, so y minus 5, right, equals, the slope here is the slope 1/2 times, right, x minus 0. See, where's the slope is here. So point slope equation means the equation here shows the slope and some point that the line is going through. So the line is going through this point 0, 5. That's why I put it there. Okay, and so we got the Cartesian equation. But this Cartesian equation is not so helpful in order to see the parametric equations. And so we're going to rewrite that a little bit. So here we can write it as a y minus 5 equals a 1/2 x. Okay? Because x minus 0 is just that, dot x. And so now at this point you got your Cartesian equation. So a couple of options from here. So one option, you can multiply right from that equation. Okay? One option, you can multiply both sides by 2 and making it 2y minus 10, right? Because I multiplied that 2 to the other side equals x. All right, so now with this equation right here, it's the same Cartesian equation, but in a more rearranged form right here. So with this rearranged forms, now we are seeing y as the independence variable, and x is the dependence variable. So from the skill we have learned throughout example 4, now I'm going to take it in and I'm going to let y equals t. I'm going to let x, okay, and so in that way x can be easily 2t minus 10. So I'm going a little bit of a rushing step here because I'm assuming that we built our skill from the previous examples already. So the skill we have learned earlier was that from a given Cartesian equation written as one variable being the dependence in terms of as an expression in terms of the independent variable. So we'll take the independent variable to equal the t parameter, and then now the dependence variable will be just that expression, but replace the independence variable with t. And so now we have our set of equations. So x of t, our set of parametric equations comes out being 2t minus 10 for x, and y of t is a t. That's how we've done it, and that's one way. That's one way. So back in what I said earlier, one graph right here can have different ways of finding the parametric equations, and this is just still within the trivial solution right here. You can also so now I'm going to erase this solution. That's just one way of how you find the parametric equations. Back to this equation right here. Y minus 5 equals 1/2 x. Okay. You can rewrite it as a y equals 1/2 x plus 5. I simply added 5 to both sides of that equation from that step right there. And now I have another Cartesian equation that came out from this, the rearranged version of that Cartesian equation we've had here. But this time, for this Cartesian equation, we are expressing y as the dependent variable and x here as being the independent variable. And so in that way, similar experience, I'm going to let x, this time, I'm going to let the independent variable being t. And so now I'm going to express my dependent variable as a function in terms of t. So 1/2 t plus 5. See, we come to a different set. See, we can come down to x of t, right? Finally come out t and y of t as a conclusion. 1/2 of t plus 5. We have come to a different, completely different set of parametric equations. All right, so one graph, we can come to multiple different ways of writing a set of parametric equations like that. All right. All right, so now we're going to just do some more enhancing examples right here. So I'm going to call it just some unnamed, unlabeled example. All right. So this is the graph. Go ahead and make a copy of that. Now pay attention to the scaling right here. And so let me zoom it in a little bit more. Okay, you don't have to draw the complete graph, but it's a sideways parabola. It has a vertex right here. Okay, and see, it goes up. It comes out each side right here by one step, and then it rises up one to the right hand side, and then it comes out 2 steps from the center line. Okay, 2 steps from the center line, so it rises up 4. So 1, 2, 3, 4 right there. Okay, so go ahead and draw that. All right. So now with that graph given, and we have seen it, okay, then you see if we're paying attention to the graph a little closely right here, it's got the vertex as -2, right, comma 0, right at that vertex right there, and it goes like this. Okay, and it's got a few other points. Now, what caught my attention is the graph here is a parabola. Okay, it's a sideways parabola. So parabola has to go with something quadratic. And then since the parabola, in my argument, since the parabola is pointing sideways, that means we have to treat x as a function of y. That's one thing for sure. So this side right here is a quadratic, has to be a quadratic. Okay, that's the idea right there. It's a parabola, so it brings up quadratic, but then being a sideways parabola, the quadratic has to be x as a function in terms of y, right? Because as different y values, right, we come up with different x values again. That's the way how I'm seeing it. All right, so now let's find out exactly what that quadratic is so that we can complete our Cartesian equation. So if we're only given, again, the fundamental here is once we're given only the graph, we've got to be able to figure out the Cartesian equation for that graph. So if we're looking at the graph a little more closely, we got these special points here, -2, comma 0, the vertex. I mentioned that on the board. We got that point right here. Okay, it's hard for me to put it right on scale right there, but right, -1, 1. Okay, and then we got -1, -1 down here. Okay, and then we got those special points right on the grid right here. So with those special points that you're seeing, 2, comma 2, okay, and then the 2, comma -2, those points right there, that is just enough to say that the graph has to be, it takes some elementary algebra to get this, but allow me to skip all of those little details like that, because I'm assuming that you've had that from your past courses, but the equation there has to be y squared, scale 1, so coefficient 1, y squared -2, simply just that. Okay, so your equation is y squared -2. That's our Cartesian equation. And so now upon realizing our Cartesian equation, then getting the parametric equations in the trivial solution is easy. Okay, I'm writing it down right here. So now in this way right here, and for the graph that we have right now, and we're kind of forced into only one way of writing the Cartesian equation that express one variable as the dependent and in terms of the other variable being the independent variable. And so now in that case right here, again, I'm going to choose the independent variable right here to be t. And so now in that way, x will just simply be t squared, because I'm substituting the independent variable with t squared -2. So that now means y of t, right, is a function of t, and then x of t can be regarded as just simply the t squared minus 2. So now our final completed set of parametric equations, one set of parametric equations among many other sets out there for the same line, for the same graph. X of t equals t squared minus 2, and y of t equals t. That's one way of how we get that. All right.